Inconsistency of Ampere's circuital law. We know Ampere's law is given like this. That is, the line integral of the magnetic field around any closed loop is equals to mu naught times the total current which is enclosed by the loop. Okay, that means if this is a conductor and it carries a current, let's say I, then there is a magnetic field which is created around this conductor. And when you take the magnetic field around this closed loop, then it should be equals to this much. Okay, so this is according to Ampere's law. Now, this Ampere's law is inconsistent when you introduce a capacitor in the circuit. So let us discuss that. Here we have a parallel plate capacitor connected to a battery. So these are the connecting wires. A current is produced by the battery and flows, and this current, right, it flows along this wire in this way. Now, if you place a magnetic needle at this point, you will find the needle is deflected. If you place here, again you will find the needle is deflected. Okay, and if you place here, tell me, will the needle deflect or not? Okay, so I'll come to that later. So first let me explain. Because the deflections of the needle, it is due to the presence of the magnetic field. According to Orsted's experiment, he says that a current carrying conductor always produces a magnetic field around itself. And because of this magnetic field, that's why the needle is deflected in this case. Similarly here, because there is a current, so the needle is deflected. But the question is, will the needle, when you place at this point, right, between the space, right, of the two parallel plate capacitor, will the needle deflect or not in this region? Okay. So, according to the knowledge that we have learned so far, we can say that this needle should not deflect. Why? Because needle is deflecting only when there is a magnetic field, and that magnetic field, it is due to the current, right? Current is the source of magnetic field. But here, do we have any electric current? No, because this space is totally empty. There is no conducting medium at all, right? But unlike in the case of a connecting wire, right? A wire is a conductor, so it contains a large number of free electrons. So the motions of those free electrons will constitute a current. But here there is no wire, there is no conductor at all. So it means the magnetic field, yes, the magnetic field at this region will be 0. Okay. So if the magnetic field at this region is equals to 0, then the Ampere's law B dot dl will be how much? Will be 0. Why 0? Because there is no current here. So the line integral of the magnetic field will be 0. Okay, because I is 0, so this is 0. So when this is 0, it means the magnetic field is 0. Okay. But when the magnetic field is 0 in this region, then that will contradict to what Ampere's has said before. Okay, if you consider any closed loop, right, starting from this part up to this part. Suppose this is my closed loop. Now this closed loop, as you can see here, it encloses this wire. That means this is the current. Okay. Now, we know very well, because of this current, then there is a magnetic field around the wire. Similarly here, because of a current passing through the wire, there is a magnetic field. But can you say that there will be no magnetic field here? Answer is no. If there is no magnetic field at this region, it means this loop will not be closed. Okay, so for any closed loop, always, the magnetic field exists. All right. So that will contradict, okay, to what Ampere's has said. So because of this reason, we say that this Ampere's law is inconsistent. Okay. Now, but actually, this magnetic needle, when you place at this region, this needle deflect. So the deflections of the needle, it should be something like there should be a current. Okay, because current, as I said, is the source of magnetic field. So if the needle at this point deflect, it means there is a current in this region. And that current, right, Maxwell named that current as displacement current. And he denotes that current by ID. So there should be a current in this region, and that current is known as displacement current. So because of this displacement current, then magnetic field will be created and this needle will be deflected. All right. Okay. Now, again, I will draw this diagram. This is my capacitor. This is a battery. Okay. So this is a current in the conducting wires. So the current in the conducting wires, right? Now I will say it as IC, which means the conduction current. But the current which is present inside the parallel plate capacitor, it is what current? It is the displacement current. Alright, okay. Now, from where does this current, displacement current come? Okay, this is a battery. You are charging the capacitor. When you charge the capacitor, then this plate of the capacitor will acquire a positive charge and this plate will acquire a negative charge. So it means the charge in the capacitor will gradually build up. So as the charge is gradually built up, it means the electric field also will gradually increase in the capacitor. So electric field here starts increasing, increasing. Because electric field is always directed from positive to negative. So because of this increasing electric field, then you will get a magnetic field. Okay, that means the needle is deflected. Okay, now because in the conducting wire, the source of magnetic field is the current. So if the source of the magnetic field in the conducting wire is a current, why not the source of magnetic field in the capacitor also is a current? Okay. So that is why this varying electric field, it should associated with some current, and that current is known as displacement current. So please remember here that the displacement current, it is usually produced by the varying electric field. Okay, so hence because of the displacement current, then Maxwell modified Ampere's law. Instead of this equation, he said this is insufficient and he modified it like this, that the line integral of the magnetic field, it should be equals to mu naught times the total current in the circuit. So the total current in the circuit, instead of I will write a sum of conduction and displacement current. Okay, so this becomes the new equations of Maxwell, and this is known as Maxwell modified law of Ampere's modified Ampere's law. Okay, or modified Ampere's equation. All right. Now, the sum of the conduction current and the displacement current always, form one property, and that property here is a continuity, which means If there is no displacement current, then the current IC will end up here only, in the wires only. But because of this displacement current, it means this is the current IC and inside it is ID. Okay? So IC and ID together, they form what? A continuous current. Okay, so please remember, outside the circuit, that means outside the capacitor, that means along the conducting wire, it is IC which produces the magnetic field, and inside the capacitor it is ID which produces the magnetic field. Okay, so in the next video we shall see about the magnitude of the displacement current.